In this video, I'll be going over 4.5 question 5. And we're asked to find a rectangle that's going to fit with inside this semicircle that has a maximum area. So the first thing we need to do is come up with an equation for area that only involves the variable x. And the way I go about doing it is I put the Cartesian coordinate system on top of the rectangle and the semicircle and find the equation of the semicircle in the easiest terms I can, which would be x squared plus y squared, which equals 15 squared. So the radius is 15. Keep in mind, they're using the value x here to be the distance of the bottom of the rectangle, which is fine. I'm kind of using x in the term of the Cartesian coordinate system. Really, this would be the radius, and the maximum radius is 15. So this is going to be 15 to minus 15, which would be important to know that really this is really x over 2. This is minus x over 2 if I'm going to use this x, which really comes in handy when we're talking about the interval of interest. So the x value can go from 0 to 30. Not just 15. So the maximum distance x can be is actually the diameter of the circle and not the radius of the circle. But it's nice that it's in this format, so I can write it as x squared plus y squared is r squared. So now I have the area is simply x times y, and I can represent y as this function and solve for y. So y equals the square root of 15 squared minus x squared. So I have area equals x times the square root of 15 squared minus x squared. So I have this nice, beautiful formula for area. Keep in mind my interval existence is going to be from 0 to 30. And I want to find the maximum area. So I need to find the derivative of a and set it equal to 0. Now in this function, it's not impossible. You can find the derivative. It's going to be a little bit ugly because we have, a function multiplied by a function that's a square root. So I'm going to have to use the product rule with the chain rule. And if I look in the book on page 283, they actually go through finding a minimum ladder length, and they come up with this expression. And they say, well, we could solve it in terms of L and take the derivative, but if we leave it in terms of L squared, it's going to be a lot easier to differentiate. And in this paragraph, they say L and L squared have the same local extremum at the same point, so they can choose to minimize or maximize L squared. And they do that using some pretty quick algebra. So we're going to do the same thing on this equation is we're going to simplify a to take the derivative and look at a squared. That's going to simply be x squared times 15 squared minus x squared. So now if I want to look at the maximum of the derivative of a squared, it's going to be the same for a, the same point. It's a lot easier to compute the derivative of a squared. So if I do that, I end up with let's just distribute this beforehand, right? So I end up with 15 squared x squared minus x to the 4th. Now if I differentiate that, what is 15 squared is 225. Multiply that by 2, I end up with 450x minus 4x cubed, and I'm going to set that equal to 0. So I'm finding the critical points of the a squared function. I can factor out an x. I'm left with 450 minus 4x squared, so that equal to 0. X equals 0, or 4x squared equals 450. Divide both sides by 4. I get x squared equals the square root of 450 over 4, which gives me 15 square root of 2 over 2. So this is my critical point of a squared, which is also going to be the critical point of a. To test if it's a maximum or minimum or not, I'm going to use the first derivative test on a squared. So if I'm looking at the interval, of course, 0 to 30. So if I plug in 1 of the derivative of a squared, if I plug in a value of 1 here, I have 450 minus 4, so that gives me a positive. And if I plug a number that's in between 15 square root of 2 over 2 and 30, I can just plug in any number here, 15, and if I do 15 cubed times 4, I end up with a really large negative number. So it's going to overpower it. So I would expect the slope to be positive and then the slope to be negative. So that verifies this is a maximum. This is just a little bit extra work to verify that this critical point is in fact a maximum and not a minimum. I could have also known that it's a quadratic in a sense, and so it's going to be opening down, and so that I have a 4th degree or a 2nd degree or whatnot polynomial, and that it opens down. There's a little bit of work to actually just go through and verify it. So this is the x value in which the maximum exists for a. You can solve back for y by plugging this in here, and you can find your y value, and that is going to be the height. So the